More than 9 decades of serving the nation. Central Board of Irrigation and Power.
Calculation of fault current. Electrical system, there are different kinds of fault. Fault may be direct contact with face to face, direct contact with earth, maybe liquid insulation failure. Calculation. Earth fault current, if you make high resistance grounding or high inductance grounding, or if you put something in the neutral circuit to limit the earth current, earth fault current, it is a different thing. But for short circuit current, there is no such limiting process. No such. Is the fault current? You must know how to calculate it, because based on that, your switchgear design, your conductor design, cable design, your everything depends on that. So you must know how to calculate.
This will decide all the selection of bus bar and
Everything. Even relay setting also. You must know how to do calculation. When you go for calculation, there are certain inputs you need to have. So calculation is a design calculation. You need to have certain inputs. What are those inputs? Those are listed here. That you need, calculate it, and how to calculate it, and what are the considerations. Why this, why not that? So those things have been listed out here. Go to the next slide. Now you see, who fits the fault? Who fits the fault? It is the generator. Because that is the source. Transformer cannot fit anything because it does not generate anything. It does not generate anything. It only passes the fault current through it. It allows the fault current without a little bit of limiting thing is there because of its inherent reactance. It limits something. Otherwise, it does not contribute anything to the fault current. Okay. Synchronous condenser. These are another synchronous machine. Then synchronous motors. Induction motor also. Induction motor also. You keep in mind. Induction motor also. Latter part, I will come how you should consider contribution from induction motor. That I will tell you. The later part. Okay. So I am first limiting myself. Contribution from synchronous machines. Now when there is a fault. When there is a fault, at the generator, how the fault current will be there. So far as generator is concerned. This is the nature. Suppose it is a 3-phase. How do you see? That day you were asking. Why this envelope?
these are
Because at the right instant of initiation of fault, you see the magnitude of the current?
very
Very high. Subsequently, it is gradually decreasing. And after some time, it is steady. It is a 3-phase fault. So generator is contributing the 3-phase fault like this.
these are the individual phases.
Three phase. You see how currents are displaced.
Frequencies in the phases.
You see how the currents are displaced right from the beginning. 120. You see when that is in peak, others are not. This one is in the reverse direction. That is in the shift is there. 120. Very interesting. This is the kind of waveform you get for the three-phase fault. Okay. So you can expect that all types of fault will lead to this kind of project in the same phase, then it will be high emission single phase. But envelope will be like this. At the right of the initiation point, magnitude is very high, then gradually decreasing, and then gradually stabilizing. Gradually stabilizing. Next slide. So you see. The initial phase, when the current is very high, that phase is called subtransient stage. It lasts for few cycles. And then it is transient phase, and finally it is synchronous.
So how does it categorize, like depending on the time? For how much time?
No,
Number of cycles.
no. Nature of wave.
Nature of waves.
Nature of wave. You will come here to see. Can you enlarge it, or you are able to see it? This is the envelope for subtransient. This is the envelope for transient. This is synchronous.
Steady state reactance we can also say.
Synchronous reaction.
Synchronous.
Don't say that steady state. Machine does not have any steady state. What is steady state? That is the synchronous. You say that it is a synchronous reaction. That is it is the same synchronous. We say we tell that it is a steady state, yes, but what it's a machine language is synchronous reactance. You use that term. These are the three reactances. There is a current envelope. Current envelope. Okay. Now how much will be the current? You can calculate it from here. Now what will be the reactance? Individual phase voltage. Individual phase voltage divided by current. Okay. Now how is the current? How much is the current? Subtransient phase. First.
Highest.
Highest you can get it from here. Divided by 2. Because it is divided by 2. Give you this much. Okay. Then divided by √2. You get RMS. Voltage, phase voltage. Divided by this current give you this subtransient reactance. Similarly for transient also. If you see, there is the magnitude. How this GH is drawn? G, this is drawn. It is just the extrapolation of this curve from here after few cycles. You see, it is yet to stabilize. It is yet to stabilize. You just extrapolate it. That is the transient phase. And then finally is steady state. This is how we are getting. Now transient current, transient phase current. How much it will be? It will be GH by 2. It is a peak value. Then divided by √2, you will get RMS value. Effective phase voltage divided by this current, you get transient reactance. Okay, these are the three reactants. Synchronous reactance, it is a steady state.
It is a peak to peak value, so
That's why it is 2 by 2.
So I divided
By 2.
Then we have to divide again by
√2. Get an RMS value.
So we have a, so for calculating reactance we have to divide for converting voltage to
This is the
RMS.
practical method of calculating. This is the practical method of calculation of transient reactance and subtract reactance. Any resistance, you see transformer winding, no load loss, you do. Load loss, you do. Then you find out how much is the reactance. Am I clear? For this also, generally also like this. Voltage by current.
So to calculate reactance, we have to consider the RMS value of the voltage, not the.
Definitely, not peak value, RMS. That is the reason it is by root 2 divided by root 2 is coming. Am I clear to you all of this?
Yes, sir.
Okay. Based on this here, these machines are rated in the nameplate, the technical sheet they said. Subtransient reactance is this much, transient reactance is this much, synchronous reactance is this much.
So they have got this value doing this calculation.
They in the test bed they have done it and then they have calculated. As you do for transformers. Generators, you do not have any access like that, so that's why you do not know. But transformer laboratory, college laboratory, you must have done the transformer load loss and no load loss based on that, how to calculate the reactance, reactance. Okay. Anything you want to ask on this particular? No.
Yes.
Then
So, like you considered that you left those 2 weeks out for the transient. You considered those 2 weeks were left out, and then from the further you took the curve. Now, how did you came to the conclusion that from this point onwards it is a transient state?
you see how peak is quickly decaying. Quickly decaying is in the subtransient. Then gradually. You see slope.
Yes.
Slope you see. Very valid question. Slope you see. Transient slope is smooth. From that point you draw extrapolate it. Draw tangent. Okay. Next. Do you have anything to ask on this?
Previous slide.
This one.
So actually,
You see, this subtransient reactance is very important because this is required to calculate the current at the initial point. Based on that, your circuit breaker rating will be decided. Protection relay setting will be decided. That's why this value has to be considered for it. Now you see, so many renewable energy will be coming to your system.
Yes, sir.
When renewable energy is not there, then what you will do?
I will opt out for any other source.
You will go to this machines only.
Yes, sir. I will.
You will go to machines only. Machines means either hydro machines
Hydro or thermal.
or thermal or nuclear, whatever. Nuclear is steady anyway. You go there. When machines are connected, then you see. Then this subtransient, any fault occurring in the system, this subtransient reactance of all the machines operating in parallel will come into picture. All the machines operating in parallel will come into picture. And when it is a parallelism, then equivalent reactance is low. Are you getting my point? The effect of parallelism in the series, it goes up, goes high, additive. But here it is reduction.